This video covers angular momentum. Remember that linear momentum, represented by the p, tells you how hard or how difficult it's going to be to stop an object. So the larger it is, the harder it is to stop, or the faster it's moving, the harder it is to stop. So angular momentum tells you how difficult it is to stop a rotating object. Now, total angular momentum is the sum of the individual angular momenta. So for angular momentum, represented by a capital letter L, it's going to be equal to r cross p. Now r is going to be your position vector, and p is going to be your momentum vector. Now, if angular momentum L is equal to r cross p, well, p is momentum, and it's represented by mass times velocity. So if mass is constant, then really what we're looking at is r cross v, that product times your mass. Now remember, every time that we do see a cross product, we want the two components to be perpendicular to each other. So in this case, they're going to be used as sine theta. So we can rewrite angular momentum as r times m times v times sine theta. Now the important thing to remember is that if you look at these components, none of them are actually rotating pieces. So an object doesn't have to be rotating in order for it to have angular momentum, and we'll see that in the first example. This example asks us to calculate the angular momentum for a 5 kilogram point particle about located at 2, 2 with a velocity of 2 meters per second east. So it's a velocity of 2 meters per second east. Our reference point in this case is O, and our mass is 5 kilograms. So, angular momentum, mvr sine theta. Our mass in this case is 5 kilograms. Our velocity is 2 meters per second. Now, there's two different ways that you can do the r. You can either say that this is the r, and for this situation, it would be 2 root 2. And the angle between this r and v would be 45 degrees. Or you can say that this point over here is already the component of r that is perpendicular to v. So this component of r would be 2 meters per second. And the angle between this r and v would be 90 degrees. So I'm going to go ahead and use that one instead. So I'm going to say that r is 2 meters, not meters per second, meters. And my angle is 90 degrees. So plugging all of that in, you get an angular momentum of 20 kilograms meters squared over seconds. Number 2 asks us to find about point P at 2, 0. For this one, again, angular momentum is mvr sine theta. M is 5, v is 2, and r from point P is already perpendicular to v. So again, we get the same situation, 2 meters with an angle of 90 degrees. So we get the same answer of 20 kilograms meters squared per second. And then part C. Says about point Q at 0, 2. Well, point Q is over here. Now, the R from Q to V is this point right here, this in purple. Now, we can see that that is in the same direction as V. So, that tells us that the angle between them is 0. So the angular momentum would be 0. Now, the situation you'll see a little bit more often is the spin angular momentum. Now, if you look at the situation where we have an object moving in a circle with some velocity v, some distance r away from the center, then the velocity that it's moving at is going to be equal to r omega. If that's true, then I can replace v with r omega. If you look at m r squared times omega, this piece is angular momentum. So when you're dealing with an object moving in a circle, then the angular momentum is equal to I times omega, which is our moment of inertia times our angular speed. So this is really where the direction part comes in. Again, you're going to be using the right hand rule. Fingers go in the direction of R, and your palm or your fingers curl in the direction of your momentum, in this case, the velocity. So your thumb is going to point in the direction of your angular velocity. So if it's pointing out of the page, it's going to be represented by a dot. And if it's pointing into the page, then it's going to be represented by a cross. So this is more likely to be seen on a multiple choice section of the AP exam. If it's asking you a conceptual question, then it'll show these symbols as out of the page and into the page. A way to help you remember this is I like to think of an arrow. That if you look at the arrow pointing towards you, let's say your eye is right here, then what you see is this point right here. So if it's out of the page or it's coming at you, you're going to see this dot. If your eye is looking at the other way, then what you're going to see is the crosshairs of the back of that arrow going into the page. Another important relationship that comes out of this equation is if we look at our change in angular momentum over some change in time, then we can rewrite this as our change in r cross p, or r cross momentum, divided by our change in time. Now, anytime you're trying to take the derivative of a cross product, it's always going to be the derivative of the first variable, which in this case is r, with respect to whatever it's taken to, cross the second variable, plus the first variable cross the derivative of the second variable. So this looks like dA, I'll use t in this case. To help you visualize that a little bit better. So anytime that's true, it's going to follow this cross product derivative that we see here. Now, if you look at what comes out of that, this r dr dt is simply velocity vector. And this derivative of momentum with respect to time, you should recognize as force. Now, what this tells us is if our velocity is in the same direction as momentum, which it will always be, then the cross product of those two components is always going to give us 0. So what we're left with is that the derivative of angular momentum with respect to time gives us r cross f, which is the sum of the torques. So the sum of the torques is equal to our derivative of angular momentum with respect to time. Now, this change in angular momentum can actually only ever come from external torques. So it's important to write that additional subscript. So the sum of the external torques gives us a change in angular momentum. So the most important thing that comes out of this is that if there are no net external torques being applied to my system, then there is no change in angular momentum. If there is no change in angular momentum, then we can say that our angular momentum is conserved, meaning that our momentum at the beginning is equal to our momentum at the end. In this example, we have an ice skater that spins with a specific angular velocity. She brings in her arms and legs closer to her body, reducing her moment of inertia to half its original value. What happens to her angular velocity? What happens to her rotational kinetic energy? So, if we look at her angular momentum, it has to be the same as it was in the beginning. Again, we don't have any net external torques happening here. There's nobody coming in and spinning her to get faster or slowing her down. So we have I omega, I naught times omega naught is equal to I omega. Her moment of inertia at the end is half what it was to begin with. That means that she has 2 times the initial angular velocity. Now, her rotational kinetic energy was 1/2 I omega naught squared to begin with, and at the end, she's going to have a rotational kinetic energy of I omega squared. Now, we just said that her moment of inertia is half of what it was originally. Now, the thing is that this omega is actually being squared. So, here we have four omega naught squared, 1/2 I omega, and then the 1/2 was already there. So if we reduce that 4 and that 2, then we have 2 times the original rotational kinetic energy. So that means we have increased our energy. So we said that our conservation of energy is going to be true if there was no work done. But here, because she had to do a force to bring her arms in, then she provided that additional increase in rotational kinetic energy. She put work into the system. Now our last example is a little lengthy. It says a horizontal platform in the shape of a circular disc rotates freely in a horizontal plane about a frictionless vertical axis. So you can imagine this disc, and this is our vertical axis. The platform has a mass of 100 kilograms, which is this platform here, and a radius of 2 meters. A student whose mass is 60 kilograms walks slowly from the rim of the disc toward its center. If the angular speed is 2 radians per second when the student is at the rim, what is the angular speed when he reaches a point? R is equal to 0.5 meters from the center. So, conservation of angular momentum, since here again we don't have any net external torques. So we want to look at the system's moment of inertia times omega naught and find what it is at the end as well. So because they are attached to one another, or they're rotating at the same rate, the omega naught's going to be the same for both the disc and the buoy. Now the moment of inertia of the disc is capital M R squared divided by 2 plus, now the buoy is standing at the rim of the disk, so its distance from the axis of rotation, is also 2 meters. So we can say that this is m capital R squared. At the end, the moment of inertia of the disk has not changed, and the moment of inertia of the boy has. And what we're trying to solve for is this omega. So, moving this entire piece to the other side, we get capital M R squared divided by 2 plus lowercase m capital R squared times omega naught divided by capital M R squared divided by 2 plus lowercase m R squared. If you plug in all of your values, you should get a angular speed of 4.1 meters per second.